what makes a computational problem tractable and what makes it hard? More precisely, what kind of symmetry makes a computational problem tractable? This question is, of course, difficult to answer in general. It is difficult to imagine a uniform notion of symmetry that would answer this question. Some success was, however, achieved by Bulatov and Zhuk recently in the restricted setting of finite domain constraint satisfaction problems. Let us define such problems. Let B be a relational structure with a finite domain then CSP of B, the constraint satisfaction problem of B, is the following computational problem. An instance consists of variables, let us say x1, x2, x3, x4, x5, and constraints about these variables that are given by the relations of B. For example, we can require that x1 and x2 are related by relation R, and x3 and x4 are related by relation R, and that x1, x2, x3 are related by a different relation of B called S. The question is there a solution to this pattern in B? That is, can we assign values to the variables in the domain of B such that all constraints become true? An example of such a problem is the three-coloring problem for graphs. We can model this problem by taking B to be a complete graph with three vertices. Now, an instance of the CSP consists of variables, and some of the variables are required to be connected by an edge. This instance, for example, has a solution in B, whereas this instance does not. It is easy to see that an instance has a solution if and only if the graph given by the instance is three-colorable. Other examples of finite domain constraint satisfaction problems are the three-set problem or solving equations over finite fields. Now, Bulatov and Zhuk showed 3 years ago that every finite domain constraint satisfaction problem is either NP-complete or polynomial time solvable. This, of course, contrasts Ladner's theorem, which states that if P is not equal to NP, then there are problems whose complexity is strictly between P and NP completeness. It is also a great achievement because it answers a conjecture of Feder and Vardy that lasted for more than 25 years. But what is really interesting about the theorem is what distinguishes those problems that are solvable in polynomial time from those which are NP-complete. Their precise theorem can be formulated as follows. If B is a finite structure with a finite signature, this has finitely many relations, then one out of two things happen. Either B has a polymorphism, that is a function on the domain of B that preserves the structure of B, which satisfies this equation, also called an identity. And then CSP of B is polynomial time solvable. Or no polymorphism of B satisfies a non-trivial, non-nested identity, as this one, for example. And the CSP of B is NP-complete. So what we have here is a mathematical dichotomy which states for finite structures, either these structures have no symmetry in the sense that they don't set, their polymorphisms don't satisfy any non-trivial, non-nested identities, or they have this particular symmetry given by this particular identity. That's a mathematical dichotomy, and Bulatov and Zhuk showed this mathematical dichotomy matches with a complexity dichotomy. In the first case, the CSP is polynomial time solvable. In the second case, the CSP is NP complete. We can therefore say the reason for tractability in this context is the symmetry given by this identity. Where else could we look for a similar mathematical dichotomy or that matches a complexity dichotomy? Structures that are infinite but omega-categorical. What does this mean? Let B be countably infinite. Then we say this omega-categorical. If the action of its automorphism group on the n tuples in B has only finitely many orbits for all n. That means that for every fixed length of tuples in B, the structure can only distinguish finitely many tuples, or it only knows finitely many different tuples. So although the structure is infinite, it has a certain finiteness property. The algebraic approach taken in the finite case also works for countably infinite omega-categorical structures. That is, the polymorphisms still of a structure still encode the complexity of its CSP. Also, or in particular, there's a uniform reason for NP hardness for omega-categorical structures. Namely, the absence of non-trivial, non-nested, or height 1, H1 identities locally is on finite sets implies that the CSP of the structure is NP hard. Moving from finite to countably infinite omega-categorical structures allows us to model computational problems that we couldn't model in the finite case. For example, the problem of deciding for a digraph whether it contains a directed cycle, or the betweenness problem, where we are given variables, say x1 to x5, of which some triples are specified. And the question is whether there exists a linear order on the variables, such that for each specified triple, the middle element becomes the middle element of the linear order. On the other hand, the CSP of an omega-categorical structure can be undecidable. This is easy to see simply because there are more omega-categorical structures than algorithms. The CSP can also be co-NP complete. This is a theorem due to Hrushovski and Grohe. And the same authors showed that the CSP of an omega-categorical structure can be co-NP intermediate assuming, of course, that such problems exist at all. However, for an interesting subclass of the class of omega-categorical structures, there is a dichotomy conjecture similar to the finite case. This conjecture was formulated by Bodirsky and myself in 2011. The formulation, as given here, is possible due to later development on the conjecture. It states the following. If B is first-order definable in a structure which is finitely bounded, that means it has some kind of finite representation, and homogeneous, that means it has a lot of symmetry. It is now not so important what these notions mean exactly, but this condition implies that the structure is omega-categorical. Then one of two things happen. Either the polymorphisms of B satisfy non-nested, that is H1 identities locally meaning on every finite set, and the constraint satisfaction problem of B is solvable in polynomial time, or there is a finite set on which B is naked, that is, there are no non-trivial identities satisfied on this finite set by its polymorphisms, and the CSP of B is NP complete. We know that this second condition here implies NP hardness, actually in this context, NP completeness of the CSP. What remains to show is that if this B has this kind of symmetry, then its CSP is polynomial time solvable. So we have the following situation. We have the class of finite structures where dichotomy holds, complexity dichotomy holds by the theorem of Bulatov and Zhuk. We have the class of omega-categorical structures where it is possible to study symmetries in terms of polymorphisms. Why? Because we know that the polymorphisms of an omega-categorical structure encode the complexity of its CSP. And we have the class in between, the class about which the conjecture talks, where we have this tool of polymorphisms available, where it's actually reasonable to expect a dichotomy conjecture. So I write dichotomy is possible. Recall that in the finite case, the complexity dichotomy followed a mathematical dichotomy. And in fact, also for omega-categorical structures, a mathematical dichotomy was proven by Bartow and myself and improved by further work from the Wonderland of Reflections and Tong van Pham. The theorem states the following. If B is an omega-categorical structure and it has some symmetry, that is, it has local H1 identities satisfied by its polymorphisms, then actually this symmetry, which is maybe a bit abstract, implies a very concrete kind of symmetry that reminds us of the finite case, implies that the structure B has a polymorphism which satisfies this identity. It's the same identity that we know from the finite, just that are unary functions composed on the outside. When we look at this picture, we're actually only interested in half of the picture, namely those structures which have a finite signature, with finitely many relations. Why? That is because if a structure B has infinitely many relations, say B consists of the domain R1, R2, and so on, then of course we could define a CSP of B. But the complexity of this CSP would depend on the names we give to the relations. So the complexity wouldn't actually be given by the mathematical structure itself, but by the names used to describe the mathematical structure. That is not what we want. Now comes the devil's idea that is the basis of our paper. Take an omega-categorical structure with an infinite signature, which is very simple. Maybe all of its relations are empty, for example. So it has all symmetries possible. Give the relations of the structure horrible names, so that it would be very difficult for an algorithm to solve the CSP. Or the CSP. It's not a proper CSP because the language is infinite. Now we encode this structure into a finite language structure while preserving most of its symmetries. This finite language structure will be mathematically nice. However, it will have to talk about the relations of the original structure, and therefore its CSP is going to be as complicated as the names of the relations in the original structure were. In our picture here, this looks as follows. We take an omega-categorical structure and we move it over from the infinite signature side to the finite signature side by an encoding that preserves symmetries and in such a way that this encoded structure can still reconstruct in a way the original structure. I'm now on the other side, on the side of finite language structures. We can imagine the encoding roughly as follows. Starting with the structure A, we add some space to A, and for every tuple in the relation of A, we add a code in this new space for the tuple, which tells us that the tuple is contained in the relation. The code looks something like this. Where this sequence, zeros and ones, is the name for the relation that we're encoding. Our encoding has the following properties. First of all, since we add something to the structure, the encoding of the structure does not have more symmetries in the form of identities than the original structure. On the other hand, the polymorphisms, or in fact only the injective polymorphisms, of the original structure almost extend to polymorphisms of the encoding, almost meaning up to a unary function that we have to apply. So the original structure and the encoded structure have similar symmetries, one can say. Finally, there's an exact correspondence, can very well describe, between the CSP of the original structure. It's not really a computational problem because it has an infinite signature, but those instances of the CSP that have solutions corresponds or can be translated in a natural way into the CSP of the encoded structure, which is an actual computational problem because the encoded structure has a finite language. Why does it have a finite language, finite signature? Because its signature only consists of these labeled arrows and some auxiliary relations, but just finitely many. It forgets the original relations. Like this, we obtain the following theorem. Let sigma be a complexity class such that co-NP to the sigma complete problems exist. Then there exists an omega-categorical structure A, whose encoding has a lot of symmetries. In particular, it has global H1 identities that are non-trivial. It is homogeneous, but the CSP of this encoded structure is co-NP to the sigma complete. As a variant of this construction, we can also obtain that the CSP of the encoded structure has co-NP intermediate complexity if such problems exist at all. For our second theorem, we encode an example, an infinite signature example that we obtained a year before of an omega-categorical structure that had local symmetries in the form of H1, local H1 identities, but no global ones. This been a long-standing open problem, but the counterexample had an infinite signature. We used our encoding to provide a finite signature example of such a structure. This is, of course, a negative result, showing that these two notions of symmetry do not coincide within the class of omega-categorical structures with a finite signature. On the positive side, the local H1 identity is satisfied by our structure of a very particular form. They are so-called dissected weak NU identities. And in the original example of the infinite, that had an infinite signature, and that showed that these two notions did not coincide, there were no concrete local H1 identities given, satisfied by the structure. Rather, it was shown indirectly that the structure had to satisfy some local H1 identities. We now obtain concrete local H1 identities, so-called dissected weak NU identities, and it could be that the local satisfaction of such identities describes the tractable case in the conjecture star about structures first order definable in homogeneous finitely bounded structures, which I stated before. Our final theorem shows that within the class of omega-categorical CSPs, no complexity class can be described by a countable set of identities. More precisely, let I be a countable set of identities, and let sigma be any non-trivial complexity class. And non-trivial, I mean, contains AC0, say, and it does not intersect all Turing degrees. Then there exists an omega-categorical structure, such that when we encode this structure using our encoding, this encoded structure satisfies the identities given by the set I. So it has these symmetries, but the encoded structure is not contained in the complexity class sigma. Therefore, complexity class sigma cannot be described by this set of identities, and it is true for any pair of complexity classes and sets of identities. This is a negative result, indicating that we will not be able to use polymorphisms to get an overview of the possible complexities of CSPs of omega-categorical structures. It could still be true that the conjecture I stated before about first-order definable structures in finitely bounded homogeneous structures is true. Let us remain hopeful. Thank you for your attention.